Welcome all for the Facilities Design and Logistics course. Again, we were discussing the discrete location problems, and today we will continue our discussion on these discrete location models. If you remember, in our previous lecture, we formulated the uncapacitated facility location problem, and in this uncapacitated facility location problem, we assume that there are m customers and n potential facility locations. So this n represents the potential facility locations. It's important to understand this the formulation for uncapacitated facility location problems, because the other models that we will discuss today, actually they are similar to this one. The decision variables that we will be using, and the constraints that we include will be similar with slight changes. And those changes are because of the problem characteristics or constraints. Okay, therefore I'm just reminding you these uncapacitated facility location problems one more time. And again, remember, in this problem we have a number of customers. I can represent these number of customers here. Usually, for example, if you are locating a warehouse which will serve different cities, you can consider these customers as the cities. Okay, and then we will have a number of potential facility locations. Sometimes these potential facility locations are identical to the customers. So if these customers represent the cities, and you are locating a warehouse, and you can locate the warehouse to the same cities at all. So the same set of cities are the locations of the customers as well as the potential facility locations. But in some questions, they are different from each other. The customers and the customer locations are different, and the alternative facility locations, they are also different. So I am representing these with green ones, the potential facility locations, and with the blue ones, the customer locations. And what we try to do is we try to select a subset of these alternative or potential locations. It can be 1, it can be 2, it can be n. You can select depending on the question, of course. If it is the best decision, you can open a facility in all potential locations. Even opening one location can be optimal decision. It depends on, because what we try to do in this problem is we try to minimize the total cost. Okay, if the total cost objective is minimized by just opening a single facility, then that's it. Okay, so what we try to do, again, we try to find the alternative facility locations, let's say this one and this one, for which we satisfy the customer demands. And one of the requirements of the problem is that the demand of all customers must be satisfied. And in order to establish a facility, we have a fixed cost which we represent by Fj, and in order to satisfy the demand of a customer, we have a cost for it, associated cost. We represent it by Cij, and this is the cost of supplying the demand of customer I from a facility which is located at site J. Okay, so this now what I am sketching can be a feasible or potential optimal solution depending on problem parameters. So I have opened these two red denoted ones, okay, facilities, and for these I need to pay the fixed cost, and then I am going to satisfy, let's say, the demand of this customer and this customer and this customer from this facility, and this one from this facility. Actually, as we discussed in our previous lecture, it is possible to satisfy a proportion of the demand of a customer from one facility and another proportion, or the remaining proportion, from another facility. So, for example, 30% of the demand I can satisfy from this facility and the remaining 70% from this one. It's possible, and for this reason we defined our decision variable related to this one as Xij as the proportion of the demand of customer I that is satisfied from facility J. Okay, so this Xij represents the proportion. But at the end, as a comment, I mean, we know that even if we say that it's a proportion, and proportion means it takes values between 0 and 1. I mean, 1 represents 100% and 0 represents nothing. Okay, so Xij will be between 0 and 1. And actually, when you solve this model, it is a property of this model. Even if you don't write this, even if you don't require it, in the optimal solution, all Xij values will be either 0 or 1. So you either satisfy nothing for a customer from a facility, or you satisfy 100% of it. So it means that such a solution, you don't need to consider such solutions in which some proportion of the demand is covered from one facility and another from another facility. In all optimal solutions, or we can say that there is an optimal solution in which the whole demand of a customer is satisfied from a single facility. Okay? So in order to formulate this problem, we simply define two decision variables. One is Xij. As I said, it is the proportion of the demand of customer I, which is satisfied from facility at site J. And another one I need to identify if there is a fixed cost or not related to opening a facility. And in order to understand it, we define a binary decision variable Yj, which takes the value of 1 if a facility is located at site J, and it takes the value of 0 otherwise. Okay, so this is, let's say, Yj is the second decision variable. And by using this, we can now write our objective function and the related constraints, which we did in our previous lecture. So our objective function is to minimize the total cost. And the total cost can be written as the cost of opening new facilities. This is the setup cost, plus the cost of satisfying the demand of the customers. So Fj times Yj, this is the fixed cost. If a facility is opened, then Yj becomes 1, so that you include this setup cost. If Yj is 0, then there is no setup cost. But on the other hand, here, if you satisfy the demand of a customer, this Xij is the proportion of that demand, and if you multiply it by the cost of satisfying 100% of demand, then you calculate the associated cost. And the constraints related to this one are actually, the first one says that all demand of the customers must be satisfied. So I'm writing this constraint for all customers. If there is such a customer and there are these two facilities satisfying some proportion of the demand of this customer, then the sum of the demand satisfied from this facility and this facility should add up to 100%. And again, since I told you that even if we don't require it, in the optimal solution, the whole demand of each customer will be satisfied by a single facility. So it means that by the help of this constraint, you will have 100% of the customers satisfied from single facilities, the open facilities. The second constraint, it can be written in two different ways. In our previous lecture, we have seen this version. which says that actually, remember what is Yj? Yj is whether a facility is located in at location J, potential location J or not. So this is Yj, right? And Xij, okay, if a facility is not located in this potential, then you cannot satisfy the customers, none of the customers from this. Therefore, if Yj is 0, this constraint makes all Xij equal to 0. And if it is 1, then Xij can be 0 or 1, depending on whether that is cheaper to satisfy from there or not. It depends on your objective function. And we are writing this constraint for all possible values of I and j. On the other hand, this version is a different version. It says that when this is written only for all j. Look, this is written for all I and j, but this is only for j. Remember, j is the alternative locations for the facility. And if a yj, again this is j, if a yj is 0, then this right-hand, this is a big number, big M. This right-hand side becomes 0, and it means that this summation also becomes 0. And what is that summation? Actually, that summation is this. This is the customer. Let's assume that these are, by the way, okay, let me write in this way. We are writing this for all j. This is, let's say, a potential facility. Okay. And then there are some alternative customers. This facility may serve or may satisfy the demand of this. But if there is no facility open this potential side, then it cannot satisfy this customer, it cannot satisfy this, it cannot satisfy this and this. So the summation of all these values will be equal to 0 in that case. You see, this summation is the summation that we satisfy the demand of different customers from the same location. Okay, so on the other hand, if Yj is equal to 1, what happens? Then this right hand side over here becomes big M, which is a very large number, which is infinity. So this constraint, this left hand side can take any value. Okay, so these two versions of the constraint, you don't need to write both of them at the same time. You can write only one of them and that version will work. And this is the so-called uncapacitated facility location problem. In this problem, we use a parameter called Cij. This Cij, we called it as the cost of satisfying the demand of customer I from a facility located at J. But how can we get that cost? How that cost is calculated? Usually this cost includes different parameters. Okay, to satisfy the demand of a customer, you need to know the amount of demand, the demand itself of that customer. But this cost must depend on the traveled distance from the facility to that customer as well. So the distance appears inside this cost. So this distance multiplied by the demand of the customer multiplied by the unit cost distance gives you the parameter, this parameter value. Okay, so don't be confused that in this location model there is no distance, it is the minimization of cost, but actually no. If a facility is closer to a customer, usually it is better, it is cheaper to satisfy that demand because that distance appears inside the cost. Okay, and this statement that I mentioned is an important property of uncapacitated facility location model. We say that Xij is the proportion of demand and it is in our model between 0 and 1. It is not a binary decision variable. It doesn't necessarily be 0 or 1. It can be 0.2, 0.5, anything in our model. But still, when you solve that model, you can find an optimal solution in which these xij values either 0 or 1. It doesn't take these 0.2, 0.5 and etc. This is a property of uncapacitated facility location models. Now let's move to another version of the problem, which is the capacitated facility location problem. Okay, so now let's formulate this problem. What is different from the first one? The difference is the capacity. Okay, now the facilities have capacities. Again, how does this capacities work? It means that, okay, still we have some customers and still we have some alternative locations for the facilities. But when you establish a facility, the capacity of that facility is equal to K. Sometimes these facilities even can be different from for each facility. So it can be K1 for this, K2 for this, K3 and K4. But the thing is, here we will assume that all these capacities are equal. Okay, so you can establish a facility of K. What is that K? K is the amount of demand that you can satisfy from this facility. So then we need the demand of the customers. So let me write, this is customer 1, this one is customer 1, and it is demand I'm going to represent by D1 is 50 units. Then this customer 2 has a demand of 100. This customer 3 has a demand of 75. And each one of these customers again have their demand values. It can be different from each other. There are 6 customers in this example. Now, if you decide to open a facility, let's say here, and if this is a parameter of the problem, it is given to you, and if this K is equal to, let's say, 200. Now, the question, can I assign this D1, D3, and D2, I mean 1, 2, and 3 customers to this facility? So if I do so, if I completely assign them to this facility, not a proportion, I am trying to satisfy all that demand, then look, 100 plus 75 plus 50, it makes 225. But the capacity of my facility is 200. So it is impossible to satisfy all demand of these 3 customers. But in this case, what can I do? For example, an alternative solution can be like this. Okay, just establish another facility here. So with that facility, satisfy this 3rd customer. How much unit? Let's say 25 unit of that customer you satisfy from here and 50 from there. Now, what is the total demand or total amount that I am satisfying from this first facility? 50 plus 100, which is 200. Now it is a feasible solution. So actually this example shows us that in the capacitated facility location problem, different than the uncapacitated version, these xij variables can take different values than 0 and 1. It can take 0.2, 0.5, so those proportions can be different than 0 or 1. Okay. Now let's formulate this problem. Actually, this formulation is very similar to the previous one. We are using the same cost parameters. Fj is the fixed cost of opening facilities. Cij is the cost of satisfying the demand. This K is a parameter which gives us the capacity of the facility. And we have another parameter in this case, which is Di, which is the demand of customer I. Okay, so this Di is the total demand of customer I. Actually, in the previous one, this parameter is not given to us in uncapacitated facility flow problem. Because we were assuming that the facilities are uncapacitated, and we formulated it in a way that we know the Cij value. Cij is the cost of satisfying all demand of the customer. Here Cij is again the same thing. It is the cost of satisfying all demand of the customer. But in order to write this capacity constraint K, I need to know the demand this time. But in the previous one, there were no capacities, there were no, and for that reason, we don't need to know what exactly the demand of the customers. Okay? So let's formulate this problem. Actually, the objective function is identical. Still, I am trying to minimize the total cost, which includes the cost of opening facilities, Fj plus Yj, and then the cost of satisfying the customers. And it is a double summation I from 1 to m and j from 1 to n, Cij multiplied by Xij. So I haven't defined here, but we exactly have the same decision variable definitions with the uncapacitated version. So let me write that definition here. We have Xij, okay, this is a continuous decision variable which shows the proportion of demand of customer I satisfied from facility J, exactly the same. And this Yj is a binary decision variable. If a facility is established in site J, it will take the value of 1, otherwise it will be 0. Okay, so this is our objective function, minimize total cost, subject to the constraints. Again, we will have similar constraints to the previous model, but some slight changes. Remember, we need to satisfy all demand. Okay, so let's consider this demand of customer I. What is that demand? That demand is Di. Okay, the demand of customer I is Di. And assume this is this customer, and we establish several facilities, and we are sending some items to this customer. So this is facility 1, this is facility I, and the number of, or the proportion of items that we are sending to this facility I is Xi1 from the first facility. This is Xi2 from the second, if we establish it. This is Xi3 and this is Xi4. These are the proportions. Okay. Then what should we write? The Xi1, okay, multiplied by Di. What is it? This Xi1 is the proportion, right? And multiplied by it is demand. It gives us the number of units that are sent to this customer from this facility. Similarly, this is Xi2 times Di. This is Xi3 times Di, and this is Xi4 times Di, the amount of material that we are sending. Then what we should have? We should have Xi1 times Di plus Xi2 times Di from all facilities, Xi4 times Di. This should be equal to Di itself. I mean the Di, the all demand must be satisfied. But now, what do we have? On the left hand side, I can write it under Di parenthesis, Xi1 plus Xi2 plus up to Xi4 equals to Di. And you can just cancel out this Di, and what do we left here on the right hand side? We have 1. So we see here that actually this demand is not necessary here as well. What we need to do, let me write the final version of the constraint, but first I need to clean up some space here. Okay. So for each customer I from 1 to m, what we are doing is we are summing up over all facilities these xij values and making that equal to 1. Okay, so this is the constraint that indicates that all demand of the customers must be satisfied. Okay, second, remember we had a constraint in the previous model which says that if a facility is not established, then it cannot be used to satisfy the demand. Let me show you that constraint. We have written two versions, this one and this one. Again, you can use exactly two of them. They are both fine, exactly the same constraints. But there is one more constraint in our model, remember? Which is the capacity constraint, K, right? So we shouldn't exceed the capacity. How can we write it? Okay, we need to think for that one a little bit, how to write it. Can I make use of this one to write it? No, I'm not sure. But maybe if I modify this one a little bit, I can write, or I can include the capacity on this one. So what? Remember, when yj is 1, okay, it means that we establish a facility in location j. And then what does it say? All demand or all items sent from this facility to all customers should be less than or equal to m. Okay, then what should I write? Just replace this m with k, because you cannot send infinitely many items. You have this capacity. Okay, but again, this xij over here, it is the proportion. But this k is the number of materials. So it is not the correct way of writing it, but actually we can modify this left hand side and include di over here. So what happens? Let me write it here. For each facility, let's consider this is a facility, and from this facility I am sending units to different customers. This one, this one, this one. Okay, this is customer 1, 2, and 3. This is facility J. So this amount over I am sending here is x1j multiplied by d1. This is x2j multiplied by d2, and this is x3j multiplied by d3. And the total amount that I am sending can be at most k. So what I am writing is x1jd1 plus x2jd2 plus x3jd3 is less than or equal to, must be less than or equal to this k. But of course, if that facility is opened, and if not, this sum should be 0. So therefore I am writing multiplying the right hand side by 0. If this is 0, then this part definitely 0. If it is 1, then this part can be at most k. So this is how we write the capacity constraint. And let me write it here in closed form. I am writing this for all facilities, and we assume that there are n potential facilities, and the summation over I from 1 to m, okay, di times x, di times xij should be less than or equal to k times yj. This is how we can write the capacity, and as you can see, the demands are used here. So therefore, in this model, yes, here we don't use demands because it cancels out, but on the next one we have this demand and xij greater than or equal to 0, we write it. And actually, xij should be less than or equal to 1 as well, but because of this constraint, none of the xij's can be greater than 1. If their summation is equal to 1, individual values cannot be more than 1. So you don't need to write this one. And also, yj's are binary decision variables, which we write in this way. Now the question is, this previous formulation is a mixed integer programming formulation. We shortly represent it as MIP, mixed integer program. And mixed integer programs are usually difficult to solve. There are no straightforward ways. But how can we solve these models? What are possible solution alternatives? I will summarize these quickly, and then we will develop a heuristic solution method. Okay? Of course, we need to know what's a heuristic as well. How can we solve it? The first solution approach, of course, should be the complete enumeration. Okay, what's complete enumeration? We have learned it in Methods of OR course. Assume that, with a simple example, let me try to explain. Assume that I have these 4 alternative sites. Okay? Then, remember, I am trying to decide on which one of these to establish. Of course, it is not possible not to establish any facilities, because if you don't establish anything, you cannot satisfy the demand, but it's a constraint. The demand must be satisfied. So it means that at least you have to open at least one facility. Okay? So which facility can it be? It can be this first one. This is one alternative, right? So what we can do, you can assume that we establish a facility here and connect all customers to this one. Now, can you calculate the cost? Yes, of course. Calculate the cost of it. And it will be your objective function. Then repeat the same thing, but this time assuming instead of the other one, we establish this facility and connected all customers to this one. And this will be another alternative solution. Calculate its objective function value. And then do the same thing for the others. So how many alternatives I have tried now? I have tried 4 alternatives, right? I have selected one of these 4 alternatives. Of course, I don't know which one is the best, so I need to try all of them. But how do we know that we only need to open one facility? Maybe we will open 2 facilities. Okay? If we want to open 2 facilities, which one it will be? It can be this one and this one, right? But it can be another alternative. It can be, for example, this one and this one. Maybe it is not that, but this one. Maybe it is not that, but let's say this one and this one. So there are different ways to select 2 facilities from these 4, and we don't know which of them is better. What we do is we try. Okay, select these 2, calculate its cost. Then select the other 2 and calculate its cost. Select the other 2 and calculate its cost. And at the end, when I evaluate all such alternatives, calculate their costs, I will select the best one, and it will be the optimal solution. And this is called complete enumeration. And for our example, remember, what are the alternatives? We can select only one of the facilities, establish only one facility, and we have 4 choices to do this. Okay? This 1 out of 4 gives you the number of choices if you want to establish one facility. If you want to establish 2 facilities, then you need to select 2 out of 4. And you can do this in 4 times 3 divided by 2 in 6 different ways. Okay, or you can select 3 out of 4, or you may want to establish a facility to each one of these alternative sites. And we don't know which or how many facilities to open is the best. So what you need to do, the total number of alternatives that you have to evaluate before identifying the optimal solution is the summation of these values, which makes 15. So for a problem in which you have 4 alternative locations, the number of solutions that you will evaluate is 15. And this can be done. Even by hand, you can do it. But let's assume that instead of 4 candidate locations for the new facilities, there are 10 candidate locations. And you can select only one of them to establish, 2 of them, 3 of them, 5 of them, up to 10 of them. Okay? And this number actually can be calculated by 2 to the power 10 minus 1. This 10 is the number of candidate locations. Okay, you don't need to calculate them separately and add them. This summation already adds to this one. And we see that when there are 10 candidate locations, the number of alternatives that you need to evaluate is 1023. And it is difficult to do by hand, but by computers you can do it. Okay, you can write a Java code, C++ code, anything, and you can calculate that value, no problem. But in real life, the number of candidate locations are really high. And assume that there are 50 candidate locations. And we want to find the best one of these by using this procedure, complete enumeration. And the total number of candidates that you need to evaluate is 1.126 multiplied by 10 to the power 15. Even with the fastest computers, this will take time. And as you can see, if I sketch a graph, okay, of these on the x-axis, let's assume that this is the number of candidate locations for the new facility, and on this y-axis, if I write the number of alternatives that you need to evaluate, then you see if you have, let's say 1, 2, 3, the number is really less. 1, 2, 3, 4, 4, it was 15, remember. And then when it is 10, this number jumped to 1023, and when it is 50, it jumped to how much? 1 billion something and etc. And it increases like this. Number of alternatives. When you increase it one more time, it will jump to a huge value. So it means that this complete enumeration, you can use it only when the number of candidate locations is less. If it is high, it is not a solution alternative. Even with the fastest computers, it will take too much time. Okay, so let's stop here and we will continue discussing these solution methods, solution alternatives in our next lecture.